Thank you. So, everything I will talk about is joint work with Sean Carroll, who's somewhere there. Yeah. So, I'm going to talk about enumeration and more precisely enumeration of maps. So, this is a classical subject in combinatorics and in FPSAC in particular. And so, people have been counting maps for years, 50 years or so, and we just found a very simple formula which is much simpler than everything that existed before. And surprisingly, this formula is just a 3-line consequence of things that were well known. Nobody noticed it before. That's what I'm going to do. So, okay, so what's a map? So here G is an integer, and the map of genus G is a graph drawn without edge crossing on the orientable surface of genus G, so with G handles, in such a way that each face is homomorphic to a polygon. So here, for example, you have a torus, so G equals 1. You have a graph drawn on it. There are two faces. One of them is a triangle, so that's fine. But the other one has a non-trivial topology. It's a torus with a hole. So this is not a right map. This, on the other hand, you could check that all the faces here are just topological polygons. So this is a valid map of genus 1. And I want to consider these objects up to homeomorphisms. So for example, these two drawings are the same map. And you can observe on my picture that I allow multiple edges and I allow moves. So that's a map. So this strange condition of wanting faces to be homomorphic to disks is maybe more concrete if you view it in that way. So if you take a map and you cut the surface along the edges of your graph, by definition you obtain a collection of polygons. So alternatively, you can see a map as a surface that you obtain by taking a family of polygons and gluing sides together. If you do that, you obtain a surface, you obtain a graph drawn on it, and this is a map. In the map, you have 4 natural integer parameters. You have vertices and edges because you have a graph. You also have faces, and you have the genus, so the number of handles of the surface. But these 4 parameters are related by Euler's formula. So actually only three parameters. Vertices plus faces is edges plus 2 minus twice the genus. Okay, and I'm going to do enumeration, and so it's the same as trees. I don't know if you see these, but same as for plane trees, I will deal with rooted maps. So meaning that there will always be an edge which is distinguished and oriented as a root. This makes enumeration more interesting. Okay, so as I said, the enumeration of maps is a classical topic. So let me just show you some classical results. So here is the number of QMG in this table is the number of maps of genus G with edges. And so if you look at the first table of this column, you have a very nice closed formula due to TUT. So you have a nice closed formula for the number of genus 0 maps, which are always called planar maps, with n edges. So this is some extreme case in some sense. You want the genus to be minimal. Another extreme case is to look at maps of genus G with the smallest possible number of edges. So it's not very difficult to see that in order to form a surface of genus G, you need to have at least 2G edges, because you need to have at least all the non-contractible surface cycles of the surface. So this is the smallest number of edges you can have, and there's also a closed formula. So here in this table, above this diagonal, everything is 0, and on the first non-zero diagonal, you have also a very nice closed formula. And well, these are actually the only cases where you have nice closed formula. So if you go further inside this triangle, it gets more and more complicated. So, but you can still say something. So Benda and Tenfield proved this very nice result. But if you fix the genus, you essentially for each fixed genus, you have some kind of closed formula to count maps. So more precisely, you fix G and you look at the generating function of maps of genus G by the number of edges. So you go through one column here, and what you have is a closed formula in the sense that this generating function is some rational fraction in terms of this rho here, which is square root of 1 minus 12z. Okay, so for example, here you have a let's say closed formula for the generating function of maps of genus 1. You also have one for the generating function of maps of genus 2, and for each genus you have such a formula that gets more and more complicated. That is extremely difficult to compute with this classical approach here, but which you can prove it exists. Okay, so this is what you can say about these things. So you have a lot of structure, but you have closed formula only if you stay close to the edges of this triangle. Another kind of classical thing, a very famous formula due to Harer and Zaghir. So the number of one-face map of genus G. So here it's again some kind of extreme case. I want my face to have only one, my map to have only one face. So I start with a single polygon, and I do it in all possible ways. And there is also a closed formula for this. By closed formula, I mean a closed recurrence formula. This is the Harer-Zaghir recurrence formula. It's very famous. So it's a three-term recurrence relation. So in particular, in genus 0, you have Catalan numbers, and if you let the genus grow for each genus, you have some polynomial times Catalan numbers. Okay, so just, I'm not going to talk about bijection, but these formulas are not easy to prove bijectively at all, because it took 37 years to Schaeffer to prove this bijectively, also 37 years here. More than 20 years here, almost. This is still open bijectively. So you have a lot of structure with these objects and these numbers, but the structure is not at all objects. Okay. So there's a lot of work to do. Okay, so here's the new result. So it's a very simple and very surprising formula, given what I said before. So we just observed that this sequence of numbers Q and G that was on my previous slide satisfy an explicit and very simple recurrence formula that enables you to compute very easy. So Q and G is the number of rooted maps of genus G with energies. And I have something like this. So yeah, Q and G in terms of QG n-1, QG -1 and -2, and a quadratic term here, which is just a simple convolution over the two variables. So I mean, if you have ever tried to count map before, this is really surprising that such a thing exists and has been unnoticed. So in particular, it enables you to compute very easily these generating functions fg, whereas as I said with other methods, it was already extremely complicated to compute say f4. Here we can compute as far as we can. And, essentially, the size of the output is the main limit. Okay, and this is because, by simple, more precisely, I mean that I'm interested in this sequence Q and G, and I have a recurrence that involves only these two parameters, Q and G. Whereas with other methods, the other methods are based on so-called loop equations. And writing this loop equation requires to add what we call catalytic parameters. So if you want to count the number of maps of genus G with energies, you cannot write a closed recurrence for this. You have to add extra parameters, and the number of extra parameters that you have goes linearly with the size of energy. So you just get equations which are impossible to solve. Here we have something so simple. And by simple, I also mean that it looks simple. It's factorized, and the coefficients are factorized, so maybe there will be a bijective interpretation. For example, I can compute this number, which is huge. Which, even like Q825 would be already very difficult with other methods. This is just a 3-minute computation. It's really much more efficient than anything that existed before. And so this is that in the FPSAC paper we figured out afterwards that we also have a 3-parameter version. So as I said, there are 3 natural free parameters in map enumeration, so genus, vertices, and edges. And we also have a very similar recursion for that. So we have mgij in terms of I-1 here, j-1 here, g-1 here, and a convolution which is a quadratic term which is just a convolution over the 3 parameters. And the interesting thing is that if we plug j equals 1 here, this convolution disappears, the equation becomes linear, and we get back the Harer-Zaghir recurrence form. And this is very unexpected for us, because so this Harer-Zaghir recurrence formula is very famous. There are lots of papers talking about it, maybe 10 different proofs, and all of them are very specific to the one-phase situation. So it's very surprising that there is just a simple extension of it that deals with all the cases. And it's actually maybe the simplest extension of it that you could hope for. There are some reasons to believe that if such an equation exists in general, it has to be quadratic. And this is like the simplest quadratic term you could think about somehow. So it's really very surprising. So what we did, so as I said, we did almost nothing to obtain this. So let me show. So we use the black box that comes from algebraic combinatorics, relates maps to integrable hierarchies, in particular case the KP hierarchy, and some simple stuff. So let me show you the simple stuff first. Okay, so it's a nice bijection of TUT. So it's, I start with a map with n edges. So here on my example, it's a planar map. And I do the following. In each face of my map, I add a white vertex, and I link it by red edges. I hope to see red. To all the corners around the face. And I do that for each face. I do that, I obtain a red map. This red map has easy properties. For example, it's bipartite. By construction, I always link black to white vertex. And it's a quadrangulation, meaning that all the faces here have degree 4. You can see it locally here. Each black edge of my original map is actually inside the face of degree 4 of my body. And this is a bijection. It's very easy. It's to tap, and it's nice. And for technical reason, it's kind of useful because you go from a problem where the degrees are unbounded to a problem where you have some bound on the degrees of the model you're considering. And from the algebraic viewpoint, this gives you some leverage on what you've done. Okay, so in other words, if I want to count map, I can just count bipartite quadrangulations. And why is this useful? Because of this black box statement. So let me do the following. I'm going to form a huge generating function. So here Z is a variable, W is a variable, and P is an infinite set of variables. Okay. F of Z, W, P1, P2, etc. So that's the generating function of all maps of all genus. So it's a huge object. All the genuses are there simultaneously. So Z is a variable that marks edges, W is a variable that marks vertices, and the PIs marks the face degrees. Okay, so more precisely, since my map is bipartite, all the face degrees have to be even because the colors alternate. So I put a variable PI for the faces of degree 2. And I form this huge object. So of course, you don't expect to have any closed formula for this object. It's just too big. There's something objects that become extremely complicated, particularly now when the genus is large. But there is some stuff coming from physics, and if you want a written reference, it's kind of hard to find. So there is a paper by Goulden and Jackson, but it was actually known before, that says that this object, so this huge object, is actually a tau function of the KP hierarchy, which in concrete terms means that it is a solution of some infinite set of partial differential equations with those variables pi. So, I mean, I'm not going to describe this infinite set, but here's some small examples. So this function is a very complicated object that satisfies some simple relations. Okay, so here F22 means I differentiate with respect to P2 twice. Here I differentiate with respect to P2 then P1. Okay, so these are just partial derivatives. These equations are quadratic. I have a square here in terms of degree 2. So this is well known, and well, nobody observed that this was it could be used to compute this number of Q edges that I showed you before. So let me show you. So actually, I only need the first of these equations. So this one is called the KP equation. And so I said this is a generating function of bipartite maps, and I want to count bipartite quadrangulations because of this stat construction I showed you. So in order to get quadrangulation, I want only faces of degree 4, so I want to set all the variables pi to 0, except for I equals to 2, and then maybe p2 to something, say 1. Okay? So if I take f, and I do this substitution, I obtain the generating function of all bipartite quadrangulations, so all maps. The only small problem is that differentiation does not commute with variable substitution. So if I take this equation and I make the substitution, I don't have a statement that concerns the generating function of quadrangulation, but a slightly different statement. And we observe that we can, that this problem is not really a problem because we can use stupid tricks to avoid it. So let me show you. So there's a term here, f11. Okay, so this means that I take f, the generating function of all bipartite maps, and I differentiate with respect to p1 twice. This means that I mark two faces of degree 2. Because differentiating is marking. And then I do my substitution. So I get something which is almost a quadrangulation, so all the faces have degree 4, but I just have two faces of degree 2 somewhere. Okay, and then I just do this simple observation that when I have in a map, if I have a marked face of degree 2, I can just contract it and I get an edge. Okay. So this is not a quadrangulation, but this is. Okay, so my generating function here, f11, after doing the substitution, the coefficients of these are just numbers of quadrangulations with maybe n1, n-1 faces instead of 1, instead of n. Okay, and some term for the marking. And of course I can do the same with f14, I just get some quadrangulation with 4 marked edges. And that's it. So there is, so we don't really understand why it works, but it works. So there is another term which is a bit more tricky. So we have an f3. So if I do the same thing with an f3, I get a quadrangulation with a marked hexagon. So it's more complicated to get rid of hexagons. Actually, we cannot get rid of hexagons, but we can get rid of one hexagon. So we do the following. I start with a rooted quadrangulation, and I look at the root edge, and I remove it. I would say that there are only two cases. So either the root edge is like this between two different faces, and if I remove it, I obtain a marked hexagon. Or it is like this, and if it's like this, so here you have a quadrangle, I contract everything and I get a marked edge. So this is a quadrangulation, this is a quadrangulation, and this is my term that was annoying me with marked edge. Okay, so I get this in terms of the two others, and I'm done. Okay, so this is. So in the end, I take this equation, and each of the 4 terms can be expressed in terms of quadrangulation. I take a coefficient, and I get a nice recurrence. This is all that we did. So of course, if you want to keep, you realize that here you can also keep track of the colors of vertices, and you get the other recurrence with one more parameter. Okay, so we don't really understand. Why we have enough freedom to add these extra equations and eliminate the things that we don't want, but we just happen to be able to do it. And so we get this very nice formula as it is. Okay, so just for our culture, let me sketch very briefly where this black box comes from. So this is actually a pure algebraic matrix. It first comes from the correspondence between bipartite maps and permutations. So if you take a bipartite map, something drawn here, so when you have a bipartite map, you have a graph, and you also have a notion of clockwise ordering of the edges of your graph around vertices, because you have an embedding in an orthogonal surface. And thanks to that, you can define a correspondence between bipartite maps and pairs of permutations. So the way you do that is you label the edges of your map in any way. So you put 1 to the root, and you put any of the n-1 factorial labelings of the other. And you build a permutation sigma white that records the counterclockwise order around white vertices, and the permutation sigma black that records the counterclockwise order around black vertices. And if you do that, you observe that the product sigma black, sigma white, so it means that you turn once around the black vertex, then once around the white one. If you iterate this, you actually see the faces of your map. And since you see, so if you know these two permutations, you have control of the vertices, white vertices, the black vertices, the faces, and also on the genus because of Euler's relation. And so this tells you that counting maps is the same as counting products of permutation in the symmetric group, and if you want to have control on the genus, on the size of the faces or degrees of vertices, you want to have control of the cycle type of this permutation. And this can be handled with the standard representation theory, so I'm not going to they do everything here, but essentially you have a group and you want to count connection coefficients. You want to look at connection coefficients between conjugate classes in this group. So this can all be expressed in terms of the characters of the group by standard foundation theory, and the characters of the symmetric group are related to symmetric functions. And so if you use only in classical knowledge about these two stuff, you get that this huge generating function of maps that I have can be expressed as an enormous sum. So I've got a log here because I want to take only connected adjectives. The sum over all partitions of something that involves Schur functions. Okay, this is because the characters of the symmetry group are involved here, so I get something in terms of Schur function. So it's a huge sum that is, that looks like you cannot do anything with it. It's just too big. You're not going to evaluate it at any point. But it has a lot of structure. Okay. And so this is called the character formula, and it's classical in matrix integral stuff. But you can do it only using like Stanley chapter 7. And that's Blackman. So this black box statement about the KP hierarchy tells you something like this. So whenever you have a generating function that can be written as a sum over all partition of a Schur function with a coefficient which has some determinantal form. This coefficient that depends on lambda on say a Jacobi-Trudi-like way. So it's a determinant of some matrix I minus lambda ij. And I don't care what M is, any matrix, any infinite matrix. Then I get that this satisfies the black box statement that I was showing you before. So this is a tau function of the KPR. Okay, and this is again an exercise for everyone in this room. So essentially, when I say that the coefficient of this sequence are determinants, I say that they satisfy some relations called the Plucker relations. And then there is something very special about this form, which is that if I make a shift of the variables, so if I substitute pi by pi plus qi, I get here something that is again of the same form, with a different matrix type. This is only a consequence of the Cauchy-Binet relations. And because of this, so I've got a generating function whose coefficient satisfies some relations, and these relations are stable by translation. And so this is exactly a differential equation. Okay, so the differential equation I showed you are nothing but some small examples of Plucker relations. And for each Plucker relation, I will get some other. Yeah, I only needed to use the smallest one. Okay, but again, what we did is, I mean, we just used this. Okay, so that's my last slide. So we have proved a very simple formula with very non-combinatorial tools. So these are characters and signs everywhere. So of course we would like to have a bijective explanation. And so this could take time, given the previous experience with maps. But I mean, it's always good when you want to do bijective combinatorics to have to know the formulas that you're going to prove. So it's hopefully this can be helpful. Yeah, I should have mentioned that there is another example where you can do this kind of elimination. So there's a similar result by Goodall and Jackson for triangulations, where the elimination part is slightly different. But there are only two cases where we know that we can do stuff like that. And we really don't understand, we don't understand why we can do this. So there's some miracle happening. For example, if I want to pick on not quadrangulation, but say exambulations, I also have all these equations. There are a lot of local manipulations that I can do, try to eliminate variables, and algebraically, we don't understand whether it has to work or not. If it doesn't work, it's strange, because this means that some unexpected miracle happened in this special case, and if it works, we still don't know. So, I guess that's it. Thank you.
similar ideas for proving their recurrences, or are you saying?
Yes, they use similar ideas, but in the case of triangulations, essentially you don't need that. It's really only local elimination of this form, and you don't need to add the extra. I mean, this is a third equation somehow, so we add an extra neat equation to the model, and they don't need that because of triangulations. And also, essentially,
my question is whether Gordon Jackson already used this kind of ideas, or are you saying that you can rederive?
No, they use it.
They did it.
They did that. So they use the KP equation for a different manipulating function, actually. Not by perfect match.
Did you get more idea from there?
Yeah, somehow. So essentially, they do something much more complicated. So what we did is, so essentially they don't phrase it that way. So if you look at their factor, you will not see that it's the same. Let's say that from this, by applying this method, what you get is a simplification of that. Yes.
You said that the sequence satisfies the whole hierarchy of equations. What happens if you try one of the higher equations rather than the first? Does something interesting still happen?
So hopefully we can, I mean, that's what I was saying in the end. So we would like to find other equations for other models. For example, with spaces of degree 6 or 8. And probably in order to do that, we have to use the higher equations plus some other tricks. But I mean, if it's possible, the higher equations will be needed. But we don't know if it's possible.
Any more questions?